Okay, we mentioned earlier that pressure is going to affect whether or not a rock can melt. So in general, when you increase the pressure on something, it makes it more difficult for it to melt. So that, for example, inside the mantle of the earth, it is extremely hot. It is way above these temperatures here that we're talking about. So inside the earth, it is definitely hot enough to be able to melt rock and turn it into magma. The problem is that the deeper you go inside the earth, the greater the pressure becomes. So that the temperature inside the mantle is saying, I want to be a liquid, but the pressure is saying, oh no, you don't, you're going to be a solid. So that inside the mantle of the earth, it's basically going to be solid rock. Now it can convect, however, extremely slowly, and it's essentially one atom at a time is slipping inside these inside the minerals that are making up the rocks inside the mantle. And so it's like one atom at a time, you have this kind of slippage is going on. And so over time periods of millions of years, you would be able to notice that the mantle is convecting, that it's moving. But if you were to look at it though, you would say that it's a solid, and that's because of the pressure. But the closer we get to the surface of the earth, the less pressure there's going to be, and so eventually we're going to reach the asthenosphere, in which the rocks will begin to melt. And then that's again going to be the source of the magma that will be able to come up. So in this particular picture here, you see that's at a mid-ocean ridge where we have material from the asthenosphere coming up, and so this is going to be liquefying due to lack of pressure, and then it can come up to the surface. Notice the pressures. So the pressure varies between 1,000 and 10,000 times the pressure that we're feeling right now. So that's the pressures inside the earth, and this corresponds to a depth of something like 10 kilometers inside the earth. Let's go ahead and do this one as well. So why does magma form? So we said temperature can do it, pressure can do it, and volatiles. So we said that the presence of water makes rocks tend to want to melt at a lower temperature. And so where and how could we have rocks that would have water in them? Well, that would be at a subduction zone. So that in the oceanic crust, that crust can absorb water from the ocean, and then those wet rocks, then as they are subducted, as they're going underneath a continental plate, for example, they're heating up, and then the presence of water in those rocks makes them melt easier, so that the lighter material floats up to the surface, and then you have your volcanic mountains as a result of this. Now, this process does not go on, for example, on the planet Venus. So on the planet Venus, it doesn't have oceans. Those oceans boiled away because Venus was too close to the sun. And so that means that the plates, and I'll put that in quotation marks, the plates on Venus do not have the water, which means that they're not going to melt as easily, which means that the plates are extra thick on Venus, which is why we think that Venus does not have the kind of plate tectonics that the Earth does. So the kind of plate tectonics where plates are pulled apart, plates are pushed together, plates slide past each other, so that does not go on the planet Venus because its lithosphere basically doesn't have any water in it, and so therefore its lithosphere is extra thick. All right, let's take a break, and when we come back, let's talk about a fourth reason why rocks tend to melt.